welcome back. So in the previous segment, I was trying to tell you how it is that scientists know what the inside of the Earth is like and how do they know what the inside of the sun is like. And I said that they use these things that are going to be called the equations of stellar structure in order to figure this out. Now, I'm just going to show them to you, and what I'd like for you to be able to do is at least recognize the letters that are in these formulas. Okay? Now, these formulas are written in terms of differential equations, so it's calculus. And so that d that you see there, dm divided by dr, you might get the idea that that d stands for distance, but in terms of what's called calculus, it's called a derivative. So you would read that equation as the derivative of m with respect to r is equal to 4 pi rho r squared. Now don't go away, okay? Come back. You don't need to pause me yet, so it's not going to be that bad. But can you recognize what the letter m stands for? So m means mass, okay? And you should recognize the letter r. So the letter r was a distance, and so that's going to be the depth inside of the Earth. So what this does is it's telling you how does the mass, the amount of mass inside the sun, change as you go deeper inside the sun. Okay, you should also recognize that symbol there, the thing that looks like the P, and I said it was called rho, and we talked about earlier in the previous unit, we said that that was density. And so it's the amount of mass divided by volume of something. So that we would need to know what's the density like inside the sun. And then once we know that, we plug it into that formula, and then we solve it using calculus, and we end up with the mass of a shell at a certain depth. Okay? Now let's go to our next one. So the next formula is called the hydrostatic equilibrium equation. So again, don't worry about these equations. It says in big bold letters up there, you do not need to know these equations for the exam. I'm just showing them to you. But you should recognize the letter P. So capital letter P stood for pressure. So this formula is going to help us to calculate the pressure at different depths inside the sun. And you should recognize big G. Big G was the gravitational constant. Because after all, what's causing the pressure inside the sun? It's the weight of all of that material. So the pressure that we're feeling here on Earth is the weight of about 500 miles of air on top of us. So the pressure inside the sun would be the weight of all of the material that's on top of that particular layer. So you can see why it would involve gravity, big G. Rho is going to be the density of the sun again, and m is going to be the mass of the sun. Okay, then the next one is going to be the energy generation equation. So you should recognize the letter L. So L was luminosity, and we said that luminosity is the power output of the sun. And so it is going to depend on the density of the sun, and it also depends on this other constant, which is called E or epsilon. So in Greek letter terminology, it's called epsilon, and it's a constant, and it's the energy generation rate of that particular star. And then the final one is, this one's going to be called the radiative transport equation. And notice that it has the letter L, so it would depend on how much energy the sun is giving off. And then it's also got some other constants in there as well. Constants for the opacity of the sun, the radiation density, and you should recognize the speed of light, c. Remember, from E equals mc squared? That's the speed of light. So these are 4 equations written in terms of calculus, and you have to solve all 4 of them at the same time. 4 equations and 4 unknowns. Because take a look at this equation. In order to be able to figure out the temperature inside the sun, well, you've got to know the luminosity of the sun. But in order to get the luminosity of the sun, you had to use this equation to get to it. And in order to use this one, you had to know the density of the sun. And in order to know the density of the sun, you got to know the mass of the sun. And in order to get the mass of the sun, you got to go back up to here and use this equation. So what you do is, hopefully you've all played around with the Microsoft Excel spreadsheet. And so what you do is you make a column in the spreadsheet for each of these 4 equations, and then you take the results of one of these equations and then you plug it into the other equations in order to solve them. And so you do it in very small increments, like an increment of distance of r of 1 kilometer, and you calculate all of these variables. And then you take all of those variables and you plug them back into the original formulas for a depth of 2 kilometers. And then you take the results of that and you plug it in for a depth of 3 kilometers. And so this would be thousands of calculations, but a computer doesn't care. So a computer would be able to do this. And so when you solve all of these equations, that's how we think that we know that the sun has these different kinds of layers associated with it. Now, is there anything that we could physically measure about the sun that would prove that our calculations are correct? And yes, there is. So do you remember that we could attach a photometer to our telescope, and that would tell us the brightness of the sun? So we would calculate what the L should be using this formula, and then we could actually measure it with the telescope, at least at the surface of the sun, to see if that was correct. We could also measure the color of the sun, and then that would tell us the temperature at the surface, and then compare that with our calculations to see if that's correct. Well, another thing that we can do is we can measure the seismic waves produced by the sun. So again, let's go back to the Earth. We said that the Earth had an inner solid iron core, outer liquid iron core, mantle, and then it had the crust. How do we know? Okay, we have set off nuclear explosions on the surface of the Earth, and also earthquakes have occurred on the surface of the Earth, and we have measured how those earthquake waves move through the Earth and then bounce off the different layers. So similarly, we can do the same thing for the sun. It turns out that every time there's a nuclear explosion that occurs inside of the sun because of nuclear fusion, it makes the sun vibrate. And it's very, very complex, but we can actually measure those vibrations and determine that the sun has different layers to it, the same way that we can use vibrations to determine that the Earth has different layers to it. And so on Earth, we're going to call this geoseismology. So geo means Earth. And when it's the sun, it's going to be called helioseismology. So the use of sunquakes in order to map the inside of the sun. So I would like for you to know that definition. What does helioseismology mean? Okay, so we're going to take a break, and when we come back, we're going to talk about in a little bit more detail about these different layers of the sun.